Today's webinar will be on high temperature testing with the guarded heat flow meter 01. During today's presentation, if you have any questions, please type them into the chat box and we will address them towards the end. At this time, I would like to pass it off to Dale.
Thank you, Mitchell. This will be a short presentation on the high temperature testing of the guarded heat flow meter. Our model is the GHFM 01. A short description of the agenda. We'll talk about thermal resistance and thermal conductivity, what they are, why temperature is important to fully characterize your material, the use of the furnace, the guard furnace, for testing specifically heterogeneous and anisotropic samples, an introduction to the GHFM 01, the typical setup for high temperature, and some results on Pyrex. So what is thermal resistance and thermal conductivity? Thermal resistance is the ratio of the temperature difference between two faces of a material to the rate of heat flow per unit. The higher the resistance, the lower the heat transfer. The lower the resistance, the higher the rate of heat transfer. This is the most appropriate characterization for heterogeneous materials, where other modes of heat transfer are present in the material. Thermal conductivity. This is intrinsic to the material. It's the ability to conduct heat. This is one of the three methods of heat transfer, the other two being convection and radiation. The higher the thermal conductivity, the higher the rate of heat transfer. The lower the thermal conductivity, the lower the rate of heat transfer. This is the most appropriate characterization of homogeneous materials when the only mode of heat transfer through a material is conduction. Why we point this out is specifically if your material is complex, means it has fillers, particles, layers, those are considered complex structures that don't fit the ideal theory of transient methods. Transient methods have very specific requirements that fit the assumptions of those, where a steady state method, which measures resistance, takes into account the total resistance between the two plates and gives you a true number when your materials are complex. So why is temperature important? Materials from different sources have a varying degree of thermal conductivity based off of when they were made, where they were made. So this is an example of two materials that are considered well understood or well known, they being aluminum and quartz. Here we have two graphs showing the change in thermal conductivity for each. I would typically, before I saw this graph, I would typically say quartz is well understood, but as you can see, the red lines representing the reference values from different sources that have been compiled into this graph, you can see they vary dramatically. That's both based off of the where the quartz was sourced and the method it was used to test. So it's really critical. The takeaway from this is it's really critical to measure your materials directly to understand their properties. Assumptions made off reference data can be dangerous and lead to use of inaccurate data. So why is thermal conductivity important, specifically with temperature, is ultimately a lot of this data gets used in thermal simulations, which is, as an input, requires one-dimensional thermal conductivity. Those simulations are typically run in steady state, one-dimensional analysis for constant thermal loads on a model to determine temperatures, heat flow rates, and heat fluxes. Of course, additional transient analysis could be performed to determine initial conditions. These values used in simulations, if you're running these with temperatures, those values can change. They can increase or decrease with temperature based off the material type, whether it be solid or liquid. The guard furnace, what's the purpose? It's to promote steady state one-dimensional heat flow. A guard is introduced to the heat flow meter to really isolate and limit the lateral heat loss caused by your material that's introduced between the two plates. It's an active guard, so it's actually heated to the mean temperature. So as your mean temperature increases, your guard would additionally change to compensate and be at that mean temperature. So if your one side of your sample, the top plate is a delta T of 30 degrees typically used. So if one side is 15 degrees higher than the mean and the other one lower 15 degrees than the mean, your guard temperature would be at that mean temperature and move along with the increase in temperature. So as you can see from these two simulations, the first one being a standard sample of stainless steel. With no guard, you have some losses due to the lateral heat loss from the sample. And with GARD on that same sample, again, that GARD is at the mean temperature. You have a much better grading across the sample. So again, you're promoting one-dimensional heat transfer from one plate through the sample to the other plate, and that promotion is really critical to the ability to measure small, higher thermal conductivity or low resistance samples. So again, this is different than the passive guarding, which we talk about with in our standard heat flow meter. This is active guarding. So the passive guarding works off of additional material on typically insulating materials. It works off the principle of extra material to promote one-dimensional heat flow, where active guarding allows you to test much smaller samples, typically 50 to 50.8 millimeters in diameter, and thickness is up to 25 millimeters. That GARD allows us to really expand the steady state method, heat flow meter method, method to higher ranges of thermal conductivity or lower resistance. Why is this function critical to heterogeneous materials? Of course, testing of homogeneous materials is possible, but very advantageous for steady state methods is for testing heterogeneous materials, where due to the additions of fillers or certain degrees of heterogeneity can create localized effects, those can cause leakage in the lateral direction. So the GARD limits the effects of this lateral leakage and gives you, again, a true one-dimensional thermal resistance and thermal conductivity. Of course, as standard with a steady state method, you have reduced sensitivity to localized heterogeneity. So if there's any distribution or poor distribution of particles or fillers or any other degree of heterogeneity, you're capturing that in the full thickness thermal resistance and calculated thermal conductivity. Transient methods should be looked at very specifically and critically when testing heterogeneous materials to see if they fit the use and ideal theory of that method. For anisotropic samples, this is probably a more critical requirement when you have layered structures or fillers that create anisotropy, which would be conduction of heat in one direction different than the other. The GARD furnace ensures that the lateral heat loss is minimized and that you, in fact, again, have one-dimensional heat flow through the sample. The result of a test with a GHFM, again, is one-dimensional thermal resistance and thermal conductivity. That's rather critical to measuring a true value through the thickness. When considering transient methods for layered structures, the requirement of anisotropic testing or even one-dimensional is that the alignment of particles or the anisotropy through the thickness is repeating and well organized. We do talk about this in other webinars, how at different time scales, if your thermal conductivity is different through the thickness, you are not following the theory of those transient methods, and you'll result in unknown thermal conductivity errors. It's really hard to put a percentage on that. It really depends on the material, but it is certainly be critical of that when you're considering measuring anisotropic samples. So layering, of course, causes anisotropic and is an important consideration. The GARD limits that and really promotes one-dimensional heat flow so that you're measuring a true value. Now let's talk about the O1. The GHFM 01 guarded heat flow meter. We're here talking about the temperature function of this meter. With this model, we can test up to 300 degrees, of course, below ambient as well. There are other functions of this method that make it quite advanced and convenient. Those are being automation of applied pressure and thickness sensing. There's an optical encoder used to measure an accurate thickness, but in the measurement and control of temperature, that can be fully automated through the software that's included with the GHFM. So that can be a convenient setup. You can save those schedules to use later so that you can have specific schedules for your materials. And if you have different materials that require different routines, those can be pulled and used to allow for convenient setup. A simple description of those setups physically would be, first, before you apply the paste, this method of course does use a contact agent or contact paste to normalize contact between the sample and the plates. You would measure the thickness of your sample. So the software asks you to insert the sample and do a dry thickness measurement. That thickness measurement is pushed through the software into the calculation, the final calculation of thermal resistance and thermal conductivity, so that when you introduce your sample with paste applied, the actual thickness of your sample is what's used, not sample plus the paste, because that does add a little bit of thickness. So for accurate results, that's the initial step. Then you would apply the paste, introduce it to the stack. The stack would automatically close. And then you can start your schedule and run your temperatures. Once your measurements are done, the data can be retrieved in the software and exported to Excel. Really the times of setups and exporting of data is minimal. Of course, the times per measurement depends on the thermal resistance of the sample. The greater the resistance, the longer it takes to reach steady state. The less the resistance, or the higher thermal conductivity, usually happens quicker. So now we can share some results or an output on a typical sample, this being Pyrex 7740. This is a well-known material, so we can measure that material and overlay the data against the literature value or the expected value. As you can see from the graph and the table, there's a percentage error reported at the bottom. The results are quite good in correlation. So this is a short introduction into the measuring of high temperature with the GHFM. There's of course a lot more we can talk about with this method, as it's very broad in its application, but I wanted to really focus on this particular function because the trends that we believe on one material aren't necessarily the same on another when it comes to temperature. So it's important to characterize. So question and answer period. We had a few questions already, one of them being how many steps of temperature can you automate through the range? That's of course really up to the user. There is no defined limit. So it really does depend on how many steps you feel you need to fully characterize your material across your material's use. What is the upper temperature range? The upper temperature range is mean of 300. So the actual temperature range of the plates can go up to 310 degrees so that you can reach a mean of 300 if that's your upper temperature. Can this function be across other types of materials and compressible materials? Yes. You can automate the pressure applied or the thickness required. You can automate that in the, again, that's one of the advanced functions of the GHFM01, is the ability to automate a thickness setting or a pressure setting, and that's done through the schedule. This could be done across a compressible material or a paste or even thin films. Okay, very good. If anybody wants to write us directly about questions for your material specifically, please feel free, and look forward to the next webinar. Thanks, everybody.